Welcome back to another episode of General Topology, and today we will talk about the category of T3 spaces, or the separation axioms for topological spaces. So I will start this lesson by recalling the basic definition of T0, T1, and T2 space. So if you recall, back then, we said a space is T0 if we have any 2 points in the space. Imagine this is the space X. If we take any 2 points A and another point B, we can separate one of them. We can find an open set containing A which does not containing B, or vice versa. We can find this is A and this is B. We can find open set that contain B but not A, which means I can separate the 2 points A and B by using an open set that contains one of them and not the other. And this is, we call it the T0 space. Later on, we define what is to be mean for a T1 space, and in short, we said that the singleton sets that contain only one element is closed. Now, this does not really match exactly the same way we define T0 by using open set, but if we look at the complement of the singleton, it means if we have a point A here, the complement will be an open set. So in a sense, I can separate A from any other point inside my space. That's the idea. It's that I want to separate any point from the rest of the points. So the rest of the points will be, of course, open set. So I can separate A far away from the other points, and this is what we call it T1 space, which is, of course, we build it on the definition of T0. So if we have T1 space, it's automatically T0 space. And then we get to the Hausdorff spaces, which is T2. This is the Hausdorff. Spaces, which allows me to do the separation of the 2 points exactly the way we wish. If we have 2 points A and B, I can separate them with 1 point, with one open set U and another disjoint set V. So this one and this one. So these two disjoint open sets will separate any 2 points A and B, and this is what we call it T2 space. Now, today in this episode, we will focus on the space T3, and in particular, if we start with the definition, I will start with defining what is a regular space, and then we'll talk about T3 space. So let me start with the regular space. We say a topological space X with a topology tau is said to be regular if for any point X in X and any closed subset. So this time the separation will be between a point and a closed subset A. There exist 2 open sets as expected. One of them is U, one of them is V, with X will belongs to U, A will be subset of V, and their intersection is empty. So if we look here, this is U, and that's exactly the definition for regular space. So if we do it geometrically, I have my big space X here, I have my point X here, and then I have, for example, a subset A here. What you will find is one open set containing X, another open set containing the whole of A, call it B, and of course they are disjoint, which means, in short, I can separate a point and a closed subset. I can separate them. Of course, my separation will be using an open set. If we have something like this, we call it a regular space. Now, why we don't call it T3 directly? Now, what's T3? Well, T3 space is a regular space, same definition. We can separate a point and a closed subset. Also, it must be T1 space. So it is regular T1 space. So I will also add that I need my singleton to be closed by themselves, because again, if we have a point Y here, I can separate it from X because it's closed. I can find a separation, and that will give me an idea. It will go through the same separation as T2, T1, as well as T0 with the same context here. So this is the definition of regular and T3 space. I can separate a point and a closed subset. That's in short. Now, what we will do next is we will explore some examples of the famous topologies that we have seen so far and check whether they are regular or not, and we'll see some properties of regular spaces. The first example is the famous Euclidean topology on the real number. Of course, the same thing will follow for the Rn. But for now, let's just focus on the real number, the real line, and let's prove, or let's show that it is T3 space. Of course, the real line is T1 space. Every point, every singleton is closed. Now, all what we need to do is we need to take 2 points, 1 point in the real number, and we need to take a closed subset of the real number. Now, just for simplicity, in this example, we will focus on the closed interval AB. So for simplicity, let A to be the closed interval A comma B. And without loss of generalization, what we will do, we will assume my point X is here and my interval lying back here. Of course, if X is in the other side, that would be fine. Of course, if X is here, we need to deal with it in a separate way, but we are assuming X and A, X not in A. So we are assuming that the separation can happen the way we expect it to happen. Now, what we need to do next is we need to find open sets that contain X. So we need to find an interval containing X. We need to find another open interval that contains AB. And those intervals, they shouldn't intersect with each other. No, the best idea is we look at the average between X and A. Of course, there will be something here between X and A, because first of all, this is closed, and this is X, we'll find something here. And next, what we will do is, we'll assume there is something, we call it Y, which is the average. Now, we take U to be this one, and V to be this one. And that's how the separation will happen, and that's how we can separate a point from a closed interval in the real line. Of course, I will keep the details for the reader, but this is the major idea of how we prove that R is a regular space. Now, we'll go to number 2, which is an interesting lemma. It says that every subspace of a regular space is regular. So in this example here, we will assume that we have a big space, we call it X, and then we have a smaller space, we call it Y, inside X. And what we know is that X is regular. Does it really mean that Y will turn out to be regular as well or not? So for that, let Y be a subspace of X. So here I'm using the subspace topology, X. We will take 2 points inside Y because now my focus will be only inside Y. So I will take 1 point Y here, and I will take another point which is a closed subset. I will call it, I don't know, maybe A. Okay. And I need to find an open set on Y and open set containing X. So let Y in V and a subset of Y be a closed subset of Y. Okay. Now there are something that we can talk about. First of all, when I'm saying Y is in Y, this is the same meaning as saying Y is already in X, because Y is subset of X. So if the small y is in the capital Y, it automatically belongs to the capital X. And what you will find that my set A can be written as A dash intersection Y, where A dash is a closed subset of X. That's how exactly the closed subset of Y looks like. Because we are in the induced subspace topology, any closed subset in Y will be a closed subset in X intersection Y. So what we got is we get a point in X and a closed subset of X. Now, because X is regular, what we find? We find there exist two open sets. One of them we will call it U dash, and the other one is V dash, such that, first of all, Y is in U dash, A dash subset of V dash, and their intersection is empty. They are disjoint. And this is all in X. So far, so good. Now, what we have is we need to find an open subset. Of course, those are open in X. Let me just write it here. Open in X. Now we need to find two subsets that are open in Y. So what we will do is set U to be equal to U dash intersection Y. And this is, of course, open in Y. The reason why, because U dash is open in X intersection Y. Same thing, we will do it for V. So it will be V dash intersection Y. Again, this is open in Y. Moreover, we have for sure that Y belongs to U. And the reason why is y belongs to u dash. Also, y belongs to y capital. So, of course, it's in the intersection, comma. A would be subset of V, and the same reason we have A dash subset of B dash, and we know that A is equal A dash intersection Y. So A is inside A dash, it's inside Y, so definitely it is inside V. And finally, of course, they don't have any disjoints. And the reason why, because U dash, V dash, the big open sets, they don't disjoint. So whatever inside them, because remember, U is inside U dash, V is inside V dash, will never be disjoint. And that's exactly how we prove lemma number 2. And that the subspace is one of the property that will be inherited. So if we have a regular space, any subspace will be also regular space. Here's the complete proof. You want to read it all at once before we move to the next example. Next example is kind of a conclusion that the integers and the rationals are regular subspaces of the real number. Of course, here there is nothing to prove. It just say we will apply lemma number 2. Because lemma number 2 said if we have a regular space or T3 space, then anything inside it, any subspace will also be regular space. What we'll do next is we'll do another example that we already saw before. And this is example number 4, Sorgenfrey line. So first of all, let me just remind you of the Sorgenfrey line. What is the topology on the Sorgenfrey line on the real number? So recall that the Sorgenfrey line is the space consists of the real number, and the topology has the basis B dash equal to the semi-closed intervals where A, of course, less than B. So here the open set looks like this. And we know that this is not connected space. We know this is a closed set. This is a closed and open in that topology. But here what we have, this is the basis. And let's see whether this is a regular space. Can we separate a point from a closed subset or not? And for that, we'll do the same thing as before. Let X be a point on the real number. And let's take A to be closed subset. And the Sorgenfrey line. So sometimes it's good practice that we draw a picture. So I will just do a picture somewhere, maybe here. So here what we have, I have my, let's suppose this is my closed subset A, and this is my set X as before. Now, what do we know about A? We know that A is closed. Hence, the complement is open. And because X is in the complement, what we can find a basis element, because this is the definition of a basis. If we take any point, we can find an open set from the basis, this point that contain it. So we can, there exists AX, BX, such that X is in this interval, AX comma BX, and this as a whole will live inside the complement. So this is exactly what we have here. Now, what we got is the following. We got my subset U, and now all I need is to find V. And what will be V? V will be, in short, this subset here, going from here to the infinity. This will be my V. Is V closed? Of course, it starts from B closed to the infinity. It's a closed subset in this free line. And is there any intersection between them? The answer is no. Now just let me formalize this in writing here. So finally, set U to be AX BX. Of course, this is open in the free line. Next, I will take V, and I will start from BX to infinity. And of course, again, this is open in the free line. And now, what we have, of course, is X belongs to U. A as a whole would be subset of Bx to the infinity. And, of course, U intersection V will definitely be empty subset. That means the free line is a regular space. And that's what we have here in example number 4. Next, what we will do next is we will want to talk about the relation between T3 and T2. Remember, we always say that T1, T0, T2, they have a relation between each other. Everyone is kind of an enhancement of the previous one. So if we have T3, it must be also T2, because each one is built on the next one. And that's exactly lemma number 5, which says that if we have a T3 space, then by default, it's a T2 space. So let's see how we will prove this one. So what we will assume, I will assume my topological space is a T3 space. Remember, T3, it means I can separate a point and a closed subset. What I want to do now is take 2 points, X and Y, in X, and I hope I can separate them. So those are the 2 points, X and Y. How we separate them? What do we know about the singleton Y? We know that the singleton Y is a closed subset. And the reason why is T2 spaces, T3 spaces is T1 space. Remember, we said it's a regular T1 space, and that's what we really needed. Okay, so what we got? We got a point X and a closed subset. So directly, we have the following. hence by the regularity of T3, what we can do, we can separate X and the closed subset. So there exist open sets U, comma V, such that X belongs to U, the singleton Y is subset of V, and if we take the intersection, is empty. Now, if we focus on this line, this is the same as saying Y is an element of V. So if we just take exactly the same thing here, just we rewrite it again. Just rewrite it again. Let me just make sure that we copy it. That's exactly, if we just put it here, and if we just do a small changes here, we get the definition. So therefore, the space X tau is T2 space, because we can separate 2 points by 2 open sets. This is a Hausdorff space, and that will give me the proof of lemma number 5. Okay, now so far so good. The final thing we want to prove or to show an example of, now what we say in lemma number 5, if we look at it all in all, what we said, if we have T3, we will get T2. Now, how about the opposite? If we have T2, is there a space which is T2 space, but not T3 space? Or they are the same, equivalent? We want to see if they are the same or equivalent, and the answer is, as expected, is no. We will have a Hausdorff space, which is not regular. Now, this space will be kind of a special space, and we will use, of course, the Euclidean topology on the real number, but we will add more open sets. So, consider the space it's called RK. Of course, when I say consider the topological space, so I have to give you my set and I have to give you my topology. Consist of, number 1, my set is the real number, and my topology or my open sets will be one of the following. The usual open intervals along with the sets of the form interval that I take away k, where k is the usual 1 over n. So my open sets in this special space will be either a normal interval, okay, or the interval that I'm taking 1 over n away from them. For example, here just an example, just to give you an example of an open set. Let me just For example, 0, 1, except K is open. Now, if you look at this set, if you do it on the number line, this set, this is 0, this is 1. This set is everywhere except half, 1 over 3, 1 over 4. Those sets, we will cancel them. We don't want them. Those points will get cancelled. We take them out. Now, whatever remaining is an open set. So this is the special one. And why we talk about this one, of course, now this is a Hausdorff space, which is T2 space. Because first of all, we didn't change the topology much. If we have 2 points, we can just put usual interval between them and we separate them. But not regular. Now the question is, why not regular? Well, if it's not regular, I will give you a point and I will give you a closed set and you will not be able to separate them. What is the point? The point will be x equal to 0 and the closed subset will be my k. 1 half, 1 over 3 and so on, which is closed set. Why it's a closed set? Because remember, the complement is open. The complement of this one will be open. Just be intervals without the k is open, so this would be an open. Of course, now why we cannot separate them? Because if we just look at how things are going up here, if this is the 0, now this set is everywhere. We cannot really separate them because whenever we try to separate them, I need to zoom in and zoom in and I need to put an interval on the 0. But once I do this, something from here will appear, definitely. I will not be able to continue. If I try to separate them, something from K must come in this side. So it cannot be really separated. And that will give me an example of a Hausdorff space, which is not a regular space. Thank you for watching. Please subscribe and like this video.